Hello, and welcome to part 3 of my NES emulation series. This video directly follows on from the previous video, so if you've not watched the earlier ones in this series, I suggest you do so now. And if you have watched the last video, then you may have picked up that I suggested this video would be about the PPU, the Picture Processing Unit. But I've had a slight change of plan, because I started to make that video and realised there's actually still quite a lot of fundamental stuff we need to understand before we can get that far. And so this video is specifically about the glue logic that binds all of the different elements of the NES together. So let's get started. We finished the last video with an implementation of the 6502 processor and a small demonstration program we could use to analyse it. That video implied that the CPU in isolation doesn't do very much, it needs to be connected to a bus. And in that demonstration we used a very simple bus that the CPU could write to and read from. Previously, I treated the entire addressable range of the CPU as a RAM. Well, on the NES, there isn't 64 kilobytes of RAM, there is in fact only 2 kilobytes of RAM. And this RAM is accessible from the range 0 to 1 FFF. Now, some of you will already have noticed that that's actually an 8 kilobyte range. So how can that range be mapped onto the 2 kilobytes of RAM that's available? Well, the NES uses something called mirroring. And this is something we'll use a lot of throughout this series. The underlying principle of mirroring is that ranges of addresses repeat. So even though the addressable range of the RAM is from 0 to 8 kilobytes, the first 2 kilobytes of that is mapped onto the hardware. Each 2 kilobyte segment of this addressable range effectively maps on to that original 2 kilobyte section, i.e. these ranges mirror the first range. So if I write to this location in RAM, I effectively also write conceptually to these locations. Naturally, the same applies when reading from the memory too. I just want to emphasise there really is only 2 kilobytes of RAM. It's just in this instance, each location of that RAM has 4 different addresses that can access it. And as I've already mentioned, we'll see this quite a lot on the NES. Fortunately, implementing mirroring is very simple indeed. Suppose I want to write to the address 0x1234. This clearly goes beyond the 2 kilobyte allowance. In decimal, this is 4660. I can perform a bitwise logic AND with the value that reflects the realistic maximum addressable range. In this case, it's 07FF, which conveniently is 2047, our 2 kilobytes. This leaves me with just the 2, 3 and the 4, which in decimal is 564, which is within our 2 kilobyte range. And this makes sense, because effectively we've done 4660 mod 2 kilobytes, which will always yield a valid address within the realistic addressable range. We know from the first video there is also another device connected to the CPU's bus. It is the PPU, the Picture Processing Unit, that handles the graphics. And I also mentioned that the PPU has its own bus. Attached to this bus is an 8 kilobyte addressable range that reflects the pattern memory. This is the memory that stores what the graphics look like, the sprites. And like the CPU, this goes from 0 to 1 FFF. There is an additional dedicated RAM here from 2000 to 2 FFF. And this stores what's called the name tables. These are effectively two-dimensional arrays which store the IDs of which patterns to show in the background. Finally, the PPU has a small RAM attached to it which stores the palette information. This describes which colours should be displayed on the screen when you combine the sprites and the background. And that goes from 3F00 to the end of the addressable range. The PPU bus doesn't have the same addressable range as the CPU bus, it's much smaller. Now you may notice something is missing here. Where is the program stored? Well, the answer's obvious, it's stored on the cartridge, that's what makes the games different. And the program ROM is addressed via the CPU bus and basically fills up the entire second half range of the CPU's addressable range. The cartridge doesn't just contain the program. It also contains all of the graphical information required to render the game. So the pattern tables are also stored on the cartridge. For simplicity, I'm going to assume that name tables are stored on the Nintendo system itself. This isn't strictly true. Certainly, there is a 2 KB RAM available to store nametable information, but some cartridges extend the feature set of the PPU bus, and some of the nametable can be stored on the cartridge. We also saw in the first video that sometimes the amount of program data required exceeds the addressable range of the CPU, and so different banks of the cartridge's ROMs need to be connected to the CPU bus as required, and this is handled by a mapping circuit, which exists on the cartridge. Mappers are typically addressed in the same range as the program ROM, because ROMs are only ever read from, but the mapper can be written to. And since the bus is capable of differentiating reads from writes, we can split the CPU's intent accordingly to either reading an instruction or some data from the ROM or configuring the mapping circuit. Just to complete this diagram, also attached to the CPU bus is the audio processing unit, access to the I/O and the controllers, and some just bits and pieces of stuff, which we'll see fleshed out in future videos. And so today I really want to build on the system architecture that allows us to define these buses and connect these peripheral devices to them. I'm also going to talk about how we can load in a cartridge and look at a system for flexibly mapping the addresses from the ROMs on the cartridge to both the CPU and the PPU. One thing to note is that all of this stuff in the middle here on the cartridge can be read and written from by the CPU and read and written from by the PPU. Our existing bus class is really going to start representing what the NES is. So over the course of this episode, we will see the bus mutate into being a representation of the console. Even though the PPU has its own bus, it's a much simpler bus. And so my PPU will contain internally the things that it needs. I'm going to work with the code that I made in the last video. I just showed that the system architecture is broadly split into 3 sections: the bus and the 6502 processor, which is what we have here, the PPU and the cartridge. So I'm going to create 2 classes, one to represent the PPU and one to represent the cartridge. For the PPU I'm going to call it OLC2CO2, which was the chip's designation. And for the cartridge I'm simply going to call it cartridge. Potentially we have lots of devices reading and writing. The CPU can read and write, and the PPU can read and write. So wherever I've got a read and write in my system, I'm going to make them quite distinctive. Only the CPU reads and writes to the bus. So I'm going to change the write and read functions to CPU write and CPU read. The bus contains the devices that are connected to it, and as we can see the CPU is already there, and we have a RAM. I'm just going to call this CPU RAM, and change the size of that RAM to 2 KB. Connected to this bus is another device, the PPU. I'm going to add a temporary variable called data to the CPU read function on the bus, and I'm going to adjust this range, which was nonsense in the last video, to something more suitable. In this case it's the 8 KB range, within which the RAM is addressed. However, we need to mirror certain RAM locations, in this case every 2 KB. So I'm going to bitwise logic AND with the value 0x7ff. as described in the slides before. Naturally, the write function looks quite similar, except from reading from the RAM, we're writing to the RAM. To the PPU header, I'm going to add 4 methods, and hopefully these should look very familiar. These 2 connect the PPU to the CPU bus, and these 2 connect the PPU to its own bus, and I'll just create some bodies for these. The main system bus is the target of all CPU writes, and here we've checked already to see if the write was targeting a RAM, but perhaps it was targeting a different address range. Let's assume it's targeting the PPU, which only has 8 addressable elements within that address range. However, the range one can write to access the PPU is much larger, and so yet again we're using mirroring to reduce this very large address range into just the 8 entries that we need. And so I'll transform the address with a logic bitwise and write the data to the PPU directly. And naturally what we'll do for write, we'll also have some symmetry in read. So far the devices I've connected to the bus exist in these fixed locations. They cannot be relocated by a mapper. In a similar way to the PPU, our cartridge class will also consist of 4 methods. because conceptually the cartridge is connected to both buses. Here are the 4 empty functions in the PPU's body, and as we had before, I'm going to create a temporary data variable and return it. The CPU can only address 8 different locations on the PPU, and in this video I'm not going to detail what these locations do, but I'm taking the address, passing it through a small switch case statement, and for now I'm going to leave it blank. They'll do nothing, but it's ready for later. Likewise, when the CPU writes to the PPU, I'm going to have another switch case statement, but leave out the functionality for now. It may be tempting to think, why not just use 8 different variables and read and write to those? But that's not quite how the transaction works in reality, because the data read back from the PPU in one location is not necessarily as the last item of data that was written to that location. And it turns out that for the PPU, just the act of reading and writing to the chip will change its state. So even though there are only 8 locations that can be transacted with the CPU, these transactions are actually quite complex. But all of that will be in the next video. And since this video isn't about the PPU, when it tries to read and write with its own bus, it's going to do nothing. So I'm just going to put in some placeholders for now. I'm masking the address, just in case the PPU ever tries to write to its bus in a location beyond its addressable range. I mentioned before that the bus is going to mutate into being the core of the emulation. It will be the class that represents the NES. And the NES very coarsely has 3 ways of interacting with it. We can insert a cartridge, which is a function that takes a shared pointer to a cartridge object. The idea being is you load the cartridge into memory before inserting it into the NES. We have a reset button on the front of the NES, and I'm providing a clock function, which is what we'll call to perform one system tick of the emulation. And I'll just get rid of this little red wiggly by including the cartridge class up here. I'm going to add one internal variable to the bus class, and this is simply going to accumulate how many times the clock function has been called. When the bus is reset, we can call the reset function on the CPU, and I'm going to set my counter to 0. The PPU also has access to the cartridge, so I'm going to store a local pointer to a cartridge object. And as I did with the bus, I'm going to create a small interface, one to connect the cartridge to the PPU, and again a clock function. The cartridge itself is effectively another device connected to the main bus. And when the bus's insert cartridge function is called, I want to connect the bus to the cartridge, and I want to connect the PPU to the cartridge. For now, this PPU connect cartridge function is very simple. We just connect its local cartridge variable to the cartridge pointer we pass in. As we have in the main bus class, the devices that are connected to it, the PPU also needs devices that are connected to its bus. But in this case, it's just memories. The first memory is the VRAM used to hold the name table information. This was 2 kilobytes, but I'm splitting this into 2 1 kilobyte chunks, because a full name table is 1 kilobyte, and the NES has the capability to store 2 whole name tables. However, it does have the ability to address 4 name tables, and we'll see that there's some trickery involved in that when we talk about the PPU in the next video. There was a RAM connected to the PPU bus that stored the palette information. There are 32 entries. Now, I'm going to add something completely unnecessary, because I'm a little strange. I'm going to add 2 4 kilobyte arrays that represent our pattern memory. This memory exists on the cartridge in normal NES systems, and normal NES emulators will do just that. And in fact, if you load up a NES game into this emulator, this memory will never be touched. However, because I'm a little strange, and I think in the future I'm going to tinker with the inner workings of the NES, because I think it will be quite a fun project to develop my own mapper, and develop some games that will only run in my emulator, yet can leverage abilities that the original NES never had. So I'm going to flag this with a little Javid future reminder. So just to recap, the PPU physically has some VRAM for the name tables, and it physically has a RAM to represent the palettes. This is not necessary, but I'm keeping it in because I might want to do some modifications in the future. Now, let's consider the cartridge. The majority of the pins on the cartridge or game pack are really just the data pins and address pins for both the CPU and the PPU. and naively we can assume there are some direct connections to some program memory and some pattern memory. Pattern memory is otherwise known as character memory, and I'm assuming the name character memory is a throwback to the days of primitive dot matrix displays where individual characters were small bitmaps in a memory somewhere. The NES operates on a similar principle, except a sprite can be made up of several bitmaps. In this case, it's a 2x2 sprite of 8x8 pixel tiles. And so I'm assuming the name just stuck. Since the pattern memory has a 3-letter name, so does the program memory. PRG. The cartridge can be a lot more sophisticated than this. Firstly, it may consist of many different memories and physically different memory chips. Or it may consist of one large memory, but only reference sections of it at a time. It is the job of the mapper to take the incoming addresses from both buses and transform them to the correct memory location on the cartridge. This way, the CPU is oblivious to the data that it's reading and writing, as is the PPU. Larger memories may be split into banks. Let's assume the CPU is addressing 0x8000. The mapper takes that 8000 and converts it into a suitable address to read from this ROM. So it could be that the 8000 really begins here, or it could be it begins here. The CPU will have pre-configured the mapper to choose which bank represents that address range. Exactly the same principle applies to the PPU. The ROM on the cartridge may be partitioned up into several different banks, and potentially all of the sprites for level 1 exist here, and all of the sprites for level 4 exist here. The program running on the CPU will configure the mapper to effectively fool the PPU into believing it's always reading from the address range 0x0000 to 1FFFF. Yet the cartridge may return different data depending on how the mapper has been configured. We'll see as we progress through the series and I add more mappers that there are a variety of different ones with different degrees of sophistication. Some added additional co-processing functionalities. Others did interesting things with sound effects. But I'm only going to stick to the most basic mappers because that covers the bulk of the library of NES games available. And this image we've built up here is not dissimilar to how the ROM file that stores the NES game content is constructed. The file has some header information that tells it how much character ROM there is and how much program ROM there is. It also contains a few other bits and pieces that the NES needs to configure its hardware. So just a quick recap, the CPU configures the mapper and the mapper translates the addresses from either the CPU bus or the PPU bus in order to read and write data to the memories contained on the cartridge. And just an aside, this is why there were really no loading times on the older consoles. Today we expect games to load all of the graphics for level 1 and then move on and it loads all of the graphics for level 2, etc, etc. On this system there's literally nothing to load. All we do is map the address line to somewhere else in this memory. And using digital electronics that's very quick and simple to do. Both the CPU and PPU are completely oblivious to the fact that that has happened behind the mapper. So to the cartridge class I'm going to add some memory. And I'm going to represent this memory in the form of vectors because I don't know how large the memories need to be until I've read the file. Fortunately for us, as the NES emulation community has matured, it's converged on a standard for representing the files that contain the information of the games. And my little ROM dumping device creates one of these files. I'm going to add to the constructor a string that represents the path to the file. And as well as my two memories for the program and character ROM, I'm also going to add three simple numbers. One, which mapper are we using? And the other two store how many banks of the respective memories there are. There is a fantastic fan resource online called the NES Cart database. Here I've found the hardware information for one of my favourite games, Disney's DuckTales, and it tells you information about the ROM, including the size and types of chips that made up the cartridge. It even has box artwork. But it also lists other interesting information we need for our emulation. It tells us which mapping circuit was adopted for this game. And don't forget, the mapper was a physical piece of hardware which translated the addresses. I'm now going to fill in the constructor for my cartridge class. The first thing I want to do is create a structure that represents the header as defined on the fantastic NES Dev Wiki. I'm then going to open the file in binary mode and immediately read in the header. The specification of the file says the next 512 bytes are used for training information. I just see this as junk, so I'm going to ignore them. Using the header that I've just read in, I can extract which mapper the ROM is using. It's a little bit convoluted, but it's entirely detailed in the file format. There are actually 3 types of iNES file, and for now all I'm interested in is type 1, but I'll leave type 0 and type 2 as placeholders for later. But in type 1, all I'm going to do is read in how many banks of memory are in the ROM for the program memory. I'm going to resize my vector to that size, and then I'm going to read the data from the file directly into the vector. And I do that for the program memory, and then I do it for the character memory. The file format standard specifies that a single bank of program memory is 16 kilobytes, and that a single bank of character memory is 8 kilobytes. These are not necessarily the same banks that the mapper will see. However, they give me the correct size for the memory that I need to read in. With the memory loaded, I'll close the file. If you were paying attention earlier, you may have noticed that my CPU read and write and PPU read and write functions for the cartridge return a boolean, whereas all of the other reads have returned the data they read. And I'm going to use this boolean to tell the calling system whether the cartridge is handling that read or write. Let's go back to the main system bus and examine the CPU write function. Right now, it assumes nothing will interfere with this address. But for my emulator, I'm going to give the cartridge first dibs on all read and writes. So here, when the bus is written to by the CPU, the cartridge gets to decide, well, hang on, that was for me. And if that returns true, then the RAM doesn't get updated, or the PPU doesn't get written to. In effect, this allows the cartridge to veto what's happening on the bus. Now, I expect in almost all cases, this is irrelevant. Why would the cartridge want to interfere with the CPU reading and writing to the CPU RAM? It wouldn't. But as before, I'm going to leave this here because it allows me to create a flexible extension to the emulator in the future, whereby just changing the mapping circuit on the cartridge, I can really change the behavior of my NES emulator. But also, if the CPU is interacting with the cartridge in a way that does matter, this returns true and it doesn't bother doing any of the other checks. So there's a small optimization to be had as well. And as before, what we do for write, we typically also do for read. I've now added the glue logic to connect the CPU bus to the cartridge. I'll do something very similar for the PPU. Even though right now our PPU doesn't do anything, I'm going to give it the option of reading from the cartridge first, or writing to the cartridge first. So now I have a framework where all reads and writes to both buses are intercepted by the cartridge, and if the cartridge isn't interested, well, they just carry on as normal to the other devices on those buses. But if the cartridge is interested, then we need to get the data from the correct location. And don't forget, we don't access that data on the cartridge directly, we go through a mapper. The NES emulation community have come together and standardized the mappers, because they're a fantastic bunch. And as you can see, there's a whole bunch of them, but the ones that we're really interested are these in the top left. In fact, for this video I'm only going to implement mapper 0, and the wiki will even specify how that mapper works. Amongst all sorts of other technical information, what we can see here is that this ROM comes in a 16 kilobyte or 32 kilobyte format, and there's only ever 8 kilobytes of character ROM. It's around about now that we're starting to get into the real technical details of implementation specifics, and these sort of things do take some digestion. If the ROM was specified as 32K, then we can see that this range represents the first half of that, and this range represents the second half of that. If it was only a 16K ROM, then this second half is a mirror of the first half. Mapper 0 is quite nice because the mapper has really no circuitry at all. But for my needs today, it will establish us with an excellent template for adding as many mappers as we need. I'm going to add a class called Mapper. When a mapper is constructed, I'm going to pass into it the number of program ROM banks and character ROM banks, and I'll store those locally. I'm then going to add 4 virtual functions, because mapper is an abstract base class. The purpose of these functions is to take the input address from the respective CPU or PPU bus and transform it into an address through which I can index the ROMs that I've read in from the file. If the address is successfully mapped, it returns true. The internals of the construction are terribly boring. And because this is an abstract class, there is nothing left to add to it. For all of the mappers I intend to implement, I'm going to derive a class from this class. So for mapper 0, I'm going to add a class called mapper, 0, 000 in this case, and I'm going to set the base class to just be mapper. And I'll add overrides for the 4 functions and give those some bodies. So don't forget, the purpose of a mapper is not to actually provide any data. It is just to translate the address. When the CPU writes to its system bus, the cartridge is only interested if the address is within the range 8000 to, the end of the range. Those locations are not satisfied by anything else in the NES, they have to come from the cartridge. So it's going to return true if the address is within that range. The same rules apply to the CPU writing. In fact, very similar rules apply to the PPU reading and writing, except the maximum range of the address is slightly smaller. In this case, encompassing the pattern tables, which were 0 to 1FFF. One of the reasons we have the mappers in these separate classes is because we can have additional variables and rules local to this specific mapper implementation. Here we are really using object-oriented program to encapsulate functionality. Now, don't forget, for mapper 0, we change the location of where we read in from our ROM file depending on how many banks are supplied in the ROM file. And here I'm doing just that. This variable contains how many 16 kilobyte chunks were loaded as program ROM. So if there's more than one of those, then we know we're working with the 32K ROM. The 32K maps into exactly half the addressable range of the 16-bit address. But we don't want to read it starting at 8000 because in the ROM file it starts at 0. So if this is a 32K ROM and the address is in the allowable range, I'm going to mask the address to ensure that we are offsetting from 0. And so I set my mapped address to that transformed input address. However, if we've only got one bank of program ROM, then this is a 16K ROM. And as we saw in the specification, we mirror the 16K ROM within that address range. And so just by changing the binary mask, as we have done earlier, we can mirror that address and return a singular mapped address to the correct location. Mapper 0 is really simple. And for the PPU, there is no bank switching at all. There is nothing to do. So the transformed address just becomes the actual address. What do we do for PPU map write? Well, the clue's in the name. It's a character ROM that we're writing to. So we don't do anything. It doesn't make any sense. So in this instance, the cartridge is not interested. It's just going to return false. It could well be the case, of course, that the cartridge doesn't just have ROM at that location, it may have RAM, in which case we would want to write to the pattern memory. That's an obscure tangent of a thought, so for now I'm just going to assume ROM is ROM. So now we're getting to the crux of the application. The cartridge has the right to intercept all reads and writes on both buses. So let's handle a CPU read. I'm going to include the mapper 0 header file in my cartridge. As I develop more mappers, I'll be including them all. And I'm also going to add a pointer to the mapper class. Once I've loaded my vectors to represent my program and character memories, I then need to load up the appropriate mapper based on the mapper ID. And so in this case, I'm using polymorphism to selectively choose which mapper class I want to use. This now leaves us with just the 4 read and write functions to the cartridge. And don't forget, these have the right to veto any transactions on both buses. I'll start by creating a temporary variable that'll hold the transformed address. But the address will only be transformed if the corresponding mapper routine for that particular bus says that the information needs to come from the cartridge. If it does, the mapped address variable now stores the offset into the ROM data I've read from the file, so I can access that data directly from my vector, and return true to indicate that the cartridge has handled that particular address. If the cartridge isn't interested, I'm just going to return false. Unsurprisingly, we have very similar routines for the other functions, except the PPU read and write functions care about the character memory rather than the program memory. Now, the content I've shown in this episode doesn't have much scope for demonstration, so I thought I'd spend the last few minutes showing how this architecture is instantiated and connected together, and lay the foundations for building the PPU in the next episode. So this is the code from the last video that displayed a memory dump and the processor status. I'm going to keep all of that, but I'm going to remove the contents from onUserCreate. I've added two variables, a pointer to the cartridge object and an object of type bus, which now represents our NES. Firstly, I'm going to load the cartridge file. Secondly, I'm going to insert the cartridge into the NES, which will connect the cartridge object to the PPU and the CPU via the bus. Because I'm still interested in the inner workings, I'm going to extract the disassembly over the addressable range. And finally, I'm going to press the reset button on the NES. I want to display the application a little differently to the user. After clearing the display, I'm going to check for some user input. In this case, if they press the C key, it's going to execute one whole instruction. And if they press the R key, it's going to reset the NES. I'm then going to draw the state of the CPU and draw some of the disassembled code as before. But I want to start getting things visual. To the PPU header file, I'm going to include the Pixel Game Engine, because inside this class I'm going to store some intermediate states that allow me to debug it and visualize its inner workings. Specifically, I'm going to add an array that will store all of the colors that the NES was capable of displaying. I've added three sprites here. One that's going to represent the full screen output, called Sprite Screen. One that's going to represent a graphical depiction of both the name tables, and one which represents the depiction of both the pattern tables. These have been sized accordingly to their layout in memory, and we'll cover that in the next episode. The NES was only capable of generating so many colours, and it adhered to a particular palette. So that palette is stored in this array, pal screen. In order to access these sprites, I'm going to add some functions which return a reference to them. Now you might be thinking, why not just access these sprites directly? Well, that's because when these functions are called, I'm going to need to construct these sprites in a particular way in order to visualize them accurately. And I don't want to do that unless I have to. I'm also going to throw in a boolean that represents when a frame is complete. And finally, I'll add in two variables, scanline and cycle. And for now, all I want you to think of these of are the scanline represents which row on the screen, and cycle represents which column of the screen. In the body of the PPU class, we'll fill in some of these obvious ones. As I've just mentioned, these functions do nothing except return the appropriate OLC sprite. But the one function we've not done anything with yet on the PPU is its clock function. The clock never stops, and every clock cycle we increase our cycle count. Now these numbers may seem a little hard-coded, but these are the physical boundaries of how the NES works. If the cycle gets to 341, we reset the cycle and increase our scanline count. If our scanline gets to 261, we set our scanline to -1 and our frame complete flag is going to be set to true. Why we set this to -1 will become clear when we start detailing the PPU. But for now, all I want you to think of this is we're scrolling across the screen in the X direction and the Y direction. Because at each location on the screen, we want to plot a pixel, and we're going to do that every time the clock function is called. So I'm just using the set pixel function of OLC sprite, using cycle and scanline as the X and Y coordinates. I'm using the palette array that we've created earlier, and randomly choosing either a black or white pixel to look like old-fashioned static noise. But from NESDev, they've provided a set of RGB values which sufficiently represent the palette entries, given a particular index. I know this all seems a little fast compared to what we've just been doing, but all of this will become clear. But I have used this colour palette information for my emulation. Every time there is a system tick, the PPU needs to do something, so it gets clocked. The CPU clock runs 3 times slower than the PPU clock. So I'm going to use my system clock counter variable to keep track of when I need to clock the CPU relative to clocking the PPU. My intention here is to keep all of my clocking information, and there's a bit more to come yet, so I can just provide a single system tick at a fast frequency, and all of the devices that care about that tick at that particular time will do their thing. But right now, it's enough to say that the CPU clock is 3 times slower than the PPU clock. Going back to our visualization, I'm going to draw the NES PPU output each frame. And whereas I have pressing the C key to execute a single instruction of the CPU, I'm going to have the F key to represent an entire frame's worth of instructions being implemented by the CPU and the PPU. Note that for both of these, I'm clocking the bus and not the device directly. And I'm almost done now, but I'm going to add 2 more variables. One is emulation run, which is a boolean, and residual time. Emulation run, if true, is going to try and run the emulation in real time, so stepping through things doesn't apply. I'm going to be sensitive to the spacebar being pressed to toggle the value of that boolean. If I am in running mode, then I'm going to do something, or I'm going to be in stepping mode. And I'm going to implement time very crudely. Fundamentally, I want to run as fast as I can. So I'm going to sit here in a loop, clocking the system until a frame is complete. This will give me a very high frame rate emulation, but it'll be barely playable. It'll be too fast. Given that I'm following the NES Dev Wiki way of doing things, and they primarily aim for NTSC based systems, and that means the frame rate of the NES should be approximately 60 Hz, 60 frames per second. So I only want to do 1 complete frame of emulation every 60th of a second. This way, it doesn't really matter how fast my emulation is, the update rate and the user interaction will be at the correct speed. And so I'm going to use my residual time variable to govern this frame rate. Let's assume residual time is set to the duration of 1 frame in real time, 1/60th of a second. Each time onUserUpdate is called, I simply decrease that value by the elapsed time. The emulation goes dormant, but once the residual time variable goes below 0, I add another whole frame's worth of time to it, minus the time of the previous frame, just to keep it a little bit accurate, and then I emulate my whole frame again. This means most of the time my emulator's not doing anything, and it does kind of assume that the emulation will be running faster than real time. So let's take a look. So now the simulation shows the output of the PPU on the left, and a small breakdown of the disassembly. And in this case, it's loaded the nestest.nes ROM, which is used for testing the 6502 CPU. Pressing the C key allows me to step through 1 instruction at a time. And we'll see we don't get very far, because the instruction it's getting stuck on is load the accumulator with the data at address 2002, which happens to be mapped into the PPU status register. So it's waiting for the PPU to get to a particular state, and since we don't have a PPU implementation that does anything, it's going to be waiting a long time. You'll notice that a cluster of pixels, which look like noise for now because that's what we told it to do, are generated per instruction. If I press the F key, we generate a whole frame in 1 hit. And if I press the spacebar, at the risk of the YouTube compression algorithm going nuts, it looks like an old television. Now, the eagle-eyed amongst you in the previous video noticed that there was a little bug in the disassembly output regarding the relative address of a branching condition. Here you can see that really we know that it's sitting in a loop waiting for the value in the accumulator to hit a certain value, but it's saying that the address it's going to jump to is somewhere way down here. It really should be jumping back to C009. So let's just quickly fix that. I'll go to the disassembler, which is at the bottom of the 6502 CPP file, and all the problem is this value was unsigned, and I'm going to make it signed. So let me just double check that that works. That looks a lot better. You can now see the relative values make sense. And so there we have it. I appreciate not a fantastically visual video this time round, but that's all going to change in the next episode when we start looking at how the NES renders its graphics. I did feel that most of the stuff in this video was necessary before we get that far though. As always, I'll upload a snapshot of this particular video code to the GitHub, and there's a link below for that. If you've enjoyed this video, a thumbs up please, have a think about subscribing, come and have a chat on the Discord server. We've opened up a dedicated emulation chat there now, and it's quite active. And finally, thanks to all of the new subscribers. I've been getting lots and lots recently, and thanks to my Patreons too. Anyway, I'll see you next time. Take care.